13.8 billion years ago, everything that would ever exist burst into being from a point smaller than an atom, or so we thought. The James Webb Space Telescope, humanity's most powerful eye on the cosmos, wasn't launched to shatter our understanding of reality. It was built to confirm the greatest story ever told about how everything began. Instead, it's revealing galaxies that formed too fast, black holes that grew too large, and structures that organized too quickly. We're about to journey through discoveries that suggest our origin story might be completely wrong. If you're ready to question everything you thought you knew about the universe, make sure to like and subscribe because the truth is stranger than fiction. Prepare yourselves. We begin. $10 billion and 30 years of planning created the most sophisticated machine ever launched into space. The James Webb Space Telescope wasn't built to surprise us. It was designed to look back through time and confirm what we already believed about the universe's birth. Scientists expected to see tiny, primitive galaxies stumbling through their first steps of formation. They anticipated finding sparse collections of early stars, barely organized into recognizable structures. Instead, Webb revealed a cosmic nightmare for everything we thought we knew. Like opening what you expect to be a baby photo album and finding portraits of fully grown adults, the telescope showed us galaxies that shouldn't exist. These weren't the cosmic toddlers we expected to find in the universe's nursery. These were massive, organized, mature systems, blazing with the light of billions of stars. Picture this. You're told a forest takes 100 years to grow, then you discover trees that are fully mature after just 10 years. That's exactly what Webb discovered in space. Galaxies that should have taken billions of years to form were already there, fully developed, just 600 million years after the Big Bang. The numbers don't just challenge our understanding, they shatter it completely. Webb's infrared eyes can pierce through cosmic dust and distance like no telescope before it. Its mirror stretches 21 feet across, gathering light that has traveled longer than any photon humans have ever captured. This gives us a time machine that reveals the universe when it was barely 3% of its current age. We expected to see cosmic infancy. We found cosmic impossibility. The telescope's discoveries have created what scientists quietly call a crisis in cosmology. Research teams around the world are scrambling to explain observations that shouldn't be possible according to our most fundamental theories. The very foundation of how we understand the universe's beginning is cracking under the weight of evidence. Every image Webb transmits back to Earth forces us to confront an uncomfortable truth. The story we've told about cosmic evolution, the narrative that won Nobel Prizes and filled textbooks, might be fundamentally wrong. We built this telescope to write the final chapter of cosmic origins. Instead, it's revealing that we might not even have the first page right. Webb was supposed to be our ultimate validator, the instrument that would put any lingering doubts about the Big Bang to rest forever. It has become our ultimate challenger, showing us a universe that refuses to follow the rules we've spent decades establishing. But this is just the beginning of what the telescope has revealed. The galaxies themselves tell an even more impossible story. 6 red dots appeared in Webb's deep field images like cosmic ghosts haunting the early universe. At first glance, these tiny specks seemed unremarkable among the thousands of galaxies scattered across the telescope's field of view. Then, astronomers calculated their distances and ages, and the impossible became undeniable. These 6 objects existed just 500 to 700 million years after the Big Bang, when the universe was still a cosmic infant. Here's what makes these discoveries so shocking. According to every model of galaxy formation we've developed, these structures simply cannot exist at that time in cosmic history. It's like finding a skyscraper in a world where only mud huts should be possible. The universe at this early stage should have been too hot, too chaotic, and too lacking in the heavy elements needed for complex star formation. Each of these 6 galaxies blazes with the combined light of billions of stars. To put this in perspective, imagine trying to build a city in 1 year using only primitive tools and raw materials. That's essentially what these galaxies accomplished on a cosmic scale. They organized billions of stars into massive, structured systems in a time frame that our best theories say should be impossible. The research team, led by astronomers from Swinburne University, published their findings in Nature and immediately sparked controversy throughout the scientific community. These aren't just slightly unexpected discoveries. They represent a fundamental challenge to our understanding of how matter behaves in the early universe. The galaxies appear so mature and organized that they seem to mock our carefully constructed timeline of cosmic evolution. Think of galaxy formation like building a house. First, you need a foundation of dark matter to provide the basic structure. Then you need gas to cool down enough to start forming stars. Finally, those stars need time to live, die, and spread heavy elements that enable more complex star formation. This process should take billions of years to create the massive, mature galaxies Webb has discovered. The 6 objects Webb found skip most of these steps entirely. They appear fully formed when the universe should barely have had time to cool down from its initial fireball. It's as if someone fast-forwarded through the first few billion years of cosmic evolution, compressing eons of slow development into a cosmic instant. But the mystery deepens when you examine exactly how massive these impossible galaxies really are. The numbers reveal something that challenges the very foundations of physics itself. One of Webb's discovered galaxies weighs more than 100 billion times the mass of our Sun. To understand how staggering this number is, consider that our own Milky Way galaxy contains roughly 60 billion solar masses of stars, and it has had over 13 billion years to accumulate this material. These early universe giants achieved even greater mass in a fraction of that time. The Milky Way is like a massive oak tree that has grown slowly over centuries, developing deep roots and a complex structure of branches. These early galaxies are like finding fully grown redwoods in a garden that was planted last week. The comparison reveals just how impossible these observations should be, according to our current understanding of cosmic evolution. Mike Boylan-Colchin from the University of Texas calculated the implications of these massive early galaxies and reached a disturbing conclusion. If these measurements are correct, we are entering completely uncharted territory in cosmology. The galaxies are so massive that they would require fundamental changes to either our understanding of galaxy formation or our understanding of the universe itself. Consider the scale of this problem. The most massive of these early galaxies contains more stellar material than galaxies that have had billions of additional years to grow and evolve. It's like discovering that a 3-year-old child weighs more than a full-grown adult. The timeline simply doesn't work with any known process of stellar and galactic development. These galaxies exist at a time when the universe was only 3% of its current age. Imagine compressing your entire adult life into just 1 year and trying to accomplish everything you've learned, built, and created in that impossibly short time frame. That's essentially what these galaxies achieved on a cosmic scale. The mass measurements come from analyzing the galaxy's light output and stellar populations. Brighter galaxies generally contain more stars, and more stars mean more mass. But these early universe objects shine so brilliantly that they suggest stellar populations that shouldn't have had time to form, let alone organize into the complex structures we observe. Current models of galaxy formation predict that building such massive systems should require at least 2 billion years under ideal conditions. These galaxies accomplished the same feat in less than 700 million years, and they did it in the hostile environment of the early universe, when conditions for star formation were far more challenging than today. The implications extend beyond just these 6 objects. If galaxies could grow this massive, this quickly in the early universe, then our entire timeline of cosmic evolution needs to be reconsidered. But the mass problem becomes even more puzzling when you examine how efficiently these early galaxies converted their raw materials into stars. For these massive early galaxies to exist, they would need to convert nearly 100% of their available gas into stars. This efficiency rate represents the absolute theoretical maximum of what's physically possible in the universe. It's like demanding that a factory achieve perfect efficiency with zero waste, using every single atom of raw material to create its final product. In today's universe, galaxies typically convert only about 10% of their gas into stars. The remaining 90% gets blown away by stellar winds, supernova explosions, and other energetic processes that prevent star formation. Think of it like trying to build a campfire in a windstorm. Most of your fuel gets scattered before it can ignite. This 10% efficiency isn't a design flaw. It's a fundamental consequence of the physics governing star formation. When massive stars die in supernova explosions, they blast enormous amounts of energy and material into space, disrupting nearby gas clouds and preventing new stars from forming nearby. This creates a natural limit on how efficiently galaxies can convert their gas into stellar material. The early galaxies Webb discovered would need to overcome all of these natural barriers to star formation. They would need stellar winds that somehow don't blow gas away. They would need supernova explosions that don't disrupt star formation. They would need a universe that operates according to completely different physical rules than the one we observe today. Achieving near-perfect efficiency would require conditions that exist right at the theoretical edge of what's possible under known physics. It's like discovering that these early galaxies found a way to violate one of the most fundamental limitations in cosmic engineering. The gas would need to collapse into stars faster than any disruptive process could scatter it. Mike Boylan-Colchin described this efficiency requirement as technically possible if everything in the early universe operated very differently from what we expect. Every single process that normally prevents star formation would need to be suppressed or eliminated entirely. Every mechanism that creates stellar feedback would need to mysteriously malfunction. Imagine trying to fill a bucket with water while someone is shooting holes in the bottom. In normal galaxies, stellar feedback creates these holes, allowing most of the gas to escape before it can form stars. These early galaxies would need buckets with no holes whatsoever, retaining and converting every single atom of available material. The efficiency problem reveals something profound about the challenge these discoveries pose to cosmology. We're dealing with galaxies that would need to operate under fundamentally different physical laws than what we observe anywhere else in the universe. The star formation process itself would need to be completely revolutionized. This near-perfect efficiency mystery deepens when we discover what else these early galaxies contain. Their centers harbor objects that pose an even greater challenge to our understanding of cosmic evolution. At the heart of these impossible early galaxies lurk supermassive black holes weighing billions of times more than our Sun. Webb has detected these cosmic monsters actively feeding and growing when the universe was less than 1 billion years old. According to our understanding of black hole formation, these objects represent an even greater impossibility than the galaxies themselves. Black holes grow by consuming matter, but there's a fundamental speed limit to this process called the Eddington limit. Think of it like trying to drink from a fire hose. There's only so much material a black hole can swallow before the intense radiation from its feeding process starts pushing away any additional food. This creates a natural throttle on black hole growth that should prevent them from reaching supermassive proportions too quickly. To grow from stellar mass black holes, which form when massive stars collapse, to the billion solar mass monsters Webb has discovered should take several billion years under ideal conditions. These early universe black holes accomplished this growth in less than 1 billion years, during a time when the universe was far more hostile to such rapid development. It's like finding a fully grown elephant in a nursery where only mice should exist. The timeline for growth simply doesn't match the available time. These supermassive black holes would need to feed continuously at or near their maximum possible rate from the moment the first stars formed, with no interruptions, no periods of starvation, and no competition from other cosmic processes. Webb discovered one quasar containing a black hole that weighs 10 billion times more than our Sun, making it the most massive black hole known in the early universe. This cosmic giant exists when the universe was still in its infancy, barely old enough to have formed its first generation of stars. The black hole alone contains more mass than most entire galaxies from that era. The presence of these early supermassive black holes creates a chicken and egg problem for cosmology. Did the black holes form first and then help create the galaxies around them? Or did the galaxies form first and then create the conditions necessary for rapid black hole growth? Either scenario requires processes that operate much faster than anything we observe in the current universe. These black holes aren't just sitting quietly in their galactic centers. They're actively accreting material and blazing forth as quasars, some of the brightest objects in the universe. Their feeding process generates so much energy that it should blow away the very gas needed for continued star formation in their host galaxies. Yet, somehow, both the black hole growth and stellar formation continue simultaneously. The discovery of these early supermassive black holes suggests that either our models of black hole formation are fundamentally flawed, or the early universe operated under very different physical conditions than we've assumed. The implications become even more startling when we examine other mysterious light sources Webb has detected in the cosmic dawn. But these supermassive black holes are just the beginning of Webb's impossible discoveries. Even stranger objects lurk in the deepest reaches of space and time. In the deepest images Webb can capture, astronomers discovered 9 sources of brilliant blue ultraviolet light, blazing from an epoch when stars shouldn't have existed yet. These mysterious objects shine from redshift 25 when the universe was only 100 million years old. At this cosmic moment, the universe should have been a dark, empty place, still recovering from its violent birth. The light sources represent the deepest observations ever made by any telescope, pushing back the boundaries of observable time by a factor of several compared to previous records. Picture trying to see individual candle flames from a distance of several miles on the darkest night imaginable. That's the equivalent of what Webb achieved in detecting these ancient light sources. 6 of these mysterious objects exist at redshift 17, when the universe was 200 million years old. 3 others shine from redshift 25, an era so early that conventional star formation shouldn't have been possible. The universe at this time was still too hot and chaotic for gas to cool down and collapse into the first stellar nurseries. Pablo Pérez González, from the Center for Astrobiology in Madrid, led the team that discovered these impossible light sources. His research pushes the boundaries of cosmic observation to their absolute limits, revealing a universe that was apparently much more active and complex in its earliest moments than any model predicted. The blue ultraviolet light these objects emit is exactly what astronomers expect from massive, hot, young stars. This creates a profound puzzle. How did these stars form so early when the physics of the early universe should have prevented their existence? It's like discovering a bonfire in a room that's supposedly too wet and cold for any flame to ignite. Some of these light sources appear point-like, suggesting they might be something even more exotic than early stars. About 30% of the objects have characteristics consistent with primordial black holes, theoretical objects that could have formed in the universe's first moments, rather than growing slowly from stellar collapse like normal black holes. If these are indeed primordial black holes, they would represent a completely different pathway for creating massive objects in the early universe. Instead of waiting for stars to form, live, die, and collapse into black holes, these objects could have existed from nearly the beginning of cosmic time, providing ready-made seeds for rapid galaxy formation. The discovery of light from redshift 25 means we're seeing the universe when it was less than 1% of its current age. At this cosmic moment, the first atoms had barely formed, and the universe was still emerging from the opaque fog that followed the Big Bang. Finding organized light sources at this epoch is like discovering a symphony orchestra performing in what should be an empty concert hall. These mysterious early light sources create yet another timeline problem for cosmology. The universe simply shouldn't have had enough time to create the conditions necessary for such bright, organized emission. The mystery deepens when we examine exactly how much time these impossible objects had to form. Current models of cosmology predict that forming massive galaxies should require at least 2 billion years under the most favorable conditions imaginable. The structures Webb discovered accomplished this feat in less than 700 million years, during the most challenging period in cosmic history. It's like watching someone complete a marathon in the time it takes to run a sprint. The 2 billion year minimum comes from fundamental physics governing how matter behaves in the expanding universe. First, dark matter needs time to clump together and create the invisible scaffolding that guides normal matter. Then gas must cool from the scorching temperatures of the early universe down to levels where it can begin forming stars. Finally, those first stars need time to live, die, and enrich space with the heavy elements necessary for more complex stellar formation. Each of these steps has its own built-in timeline that cannot be significantly accelerated without violating known physical laws. Dark matter clumping follows gravitational dynamics that operate at predictable speeds. Gas cooling depends on thermodynamics and the expansion rate of the universe. Stellar evolution proceeds according to nuclear fusion rates that are among the most precisely understood processes in physics. Think of galaxy formation, like cooking a complex meal that requires multiple steps to be completed in sequence. You can't skip the preparation time, you can't rush the cooking process, and you can't combine certain steps without ruining the final result. The universe appears to have somehow prepared this cosmic feast in a fraction of the time the recipe demands. The 700 million year time frame Webb's galaxies had available becomes even more constraining when you consider the hostile conditions of the early universe. Gas temperatures were much hotter, making star formation more difficult. The universe was denser, creating more turbulent conditions. Heavy elements were virtually non-existent, limiting the types of stars that could form. Under these challenging early conditions, galaxy formation should have taken longer than the 2 billion year minimum, perhaps 3 or 4 billion years. Instead, Webb discovered fully formed, massive galaxies that somehow overcame every obstacle and timeline constraint that should have prevented their existence. Cosmologist Catherine Nelson explained the fundamental problem. Our cosmological theory predicts that galaxies of this mass should take much longer to assemble. The timeline mismatch isn't a small discrepancy that could be explained by measurement error or minor theoretical adjustments. It represents a factor of 3 difference between prediction and observation. The time problem extends beyond just these specific galaxies. If the universe could form such massive structures so quickly in its early epochs, then our entire understanding of cosmic evolution needs to be reconsidered. The carefully constructed timeline of cosmic history, supported by decades of observations and theoretical work, begins to crumble under the weight of Webb's discoveries. This temporal impossibility becomes even more puzzling when we examine other measurements that refuse to align with our cosmic timeline. The very expansion of the universe itself seems to be telling conflicting stories about cosmic history. The universe is expanding, but astronomers can't agree on how fast. This disagreement, known as the Hubble tension, represents one of the most significant crises in modern cosmology. Different measurement methods yield expansion rates that differ by enough to suggest something fundamental is wrong with our understanding of cosmic evolution. When astronomers measure the expansion rate using nearby supernovae and other local cosmic objects, they get a value of about 73 kilometers per second per megaparsec. When they calculate the expansion rate using the cosmic microwave background radiation from the early universe, they get about 67 kilometers per second per megaparsec. This 6-unit difference might sound small, but it's far too large to be explained by measurement errors. Think of it like 2 different rulers that give you different measurements for the same object. One ruler consistently shows the object as 10 inches long, while the other consistently shows it as 11 inches long. The difference is systematic and significant enough to suggest that something is fundamentally wrong with one of your measuring tools, or with your understanding of what you're measuring. The Hubble tension has persisted for over a decade, despite increasingly precise measurements from multiple independent research teams. Webb's observations have now confirmed and reinforced the higher expansion rate values, ruling out the possibility that previous measurements were biased by instrumental errors or systematic problems with the local universe. Adam Rees, who won the Nobel Prize for discovering that the universe's expansion is accelerating, led the latest Webb study that verified the higher expansion rate. His team used the largest sample of Webb data collected over the telescope's first 2 years to confirm that the local universe really is expanding faster than the early universe measurements predict it should. This expansion rate disagreement creates a temporal paradox that compounds the timeline problems Webb has revealed with early galaxy formation. If the universe expanded faster in its early epochs than we thought, it would provide more time for structure formation. However, it would also require new physics to explain why the expansion rate was different then than now. The tension might be resolved by introducing new components to the early universe, such as early dark energy that gave cosmic expansion an unexpected boost shortly after the Big Bang. Alternatively, it might require exotic particles, changing fundamental constants, or primordial magnetic fields that operated differently in the cosmic past. Mark Kamionkowski from Johns Hopkins University suggests that resolving the Hubble tension could reveal new insights into other discrepancies with the standard cosmological model that have emerged in recent years. The expansion rate problem might be connected to the massive early galaxies Webb discovered, both pointing toward missing physics in our cosmic models. The Hubble tension represents more than just a measurement disagreement. It suggests that our understanding of cosmic expansion, cosmic time, and cosmic evolution might be incomplete or incorrect. When combined with Webb's discovery of impossible early galaxies, it paints a picture of a universe that refuses to follow the rules we've established for it. But the timeline problems run even deeper when we examine the large-scale structure of these early galaxies. They show levels of organization that shouldn't have been possible in the chaotic early universe. The early universe should have been a chaotic, turbulent place, where matter was just beginning to clump together under gravity's influence. Webb's observations reveal instead a cosmos that was surprisingly organized and structured, with galaxies showing clear patterns and arrangements that suggest a level of cosmic sophistication that shouldn't have existed yet. Many of the distant galaxies Webb discovered have flattened oval disk shapes and elongated tube-like structures, rather than the irregular, chaotic blobs we expected to find. It's like discovering that a construction site filled with scattered building materials has somehow organized itself into neat rows of completed houses while no one was watching. These organized structures require time and stable conditions to develop. In today's universe, galaxies develop their characteristic shapes through billions of years of gravitational interactions, mergers, and evolution. The early galaxies Webb discovered show these same sophisticated structures when the universe was barely old enough for the first stars to form. Think of galaxy formation like choreographing a complex dance. In the early universe, the dancers should still be stumbling around, learning their basic steps, and occasionally bumping into each other. Instead, Webb discovered cosmic dancers performing intricate routines with precision and coordination that suggests they've been practicing for eons. The level of structural organization Webb observes requires what cosmologists call dynamical relaxation, a process where gravitational interactions gradually organize matter into stable, predictable patterns. This process operates slowly, requiring many orbital periods and gravitational encounters to create the smooth, organized structures we observe in mature galaxies. Simon Lilly from ETH Zurich discovered that early galaxies had already created vast bubbles of ionized gas, extending 2 million light-years around themselves. These bubbles represent another form of large-scale organization that requires coordinated star formation and energy output across enormous cosmic distances. The creation of these ionization bubbles requires not just individual galaxies forming stars, but entire regions of space working together in a coordinated fashion. The young stars in these galaxies pumped out enormous amounts of ultraviolet radiation that cleared the surrounding gas, creating transparent regions in what should have been an opaque early universe. Coordinating this process across millions of light years requires a level of cosmic organization that conflicts with our understanding of the early universe as a chaotic, turbulent environment. It's like discovering that a newborn baby has already learned to speak in complete sentences and solve complex mathematical problems. The smooth, organized structures Webb discovered suggest that either the early universe was far more mature and stable than we believed, or that the processes governing structure formation operate much faster than our models predict. Both possibilities require fundamental revisions to our understanding of cosmic evolution. These organizational mysteries deepen when we examine the specific physical conditions that should have prevented such rapid structure formation. The early universe presented numerous obstacles that should have slowed or prevented the development of organized galactic structures. In the early universe, gas temperatures were scorching hot, creating conditions that should have prevented galaxy formation entirely. The cosmic gas that eventually becomes stars needs to cool down significantly before gravity can overcome thermal pressure and collapse matter into stellar nurseries. Webb's massive early galaxies somehow formed despite these prohibitively hot conditions. Imagine trying to build a snowman during a heat wave when temperatures are over 100 degrees Fahrenheit. The snow melts faster than you can pack it together, making construction impossible. That's essentially what galaxy formation faces in the early universe, where gas temperatures were thousands of degrees hotter than the cosmic background temperature today. Hot gas has high thermal pressure that resists gravitational collapse. The faster gas molecules move due to high temperatures, the more they resist being compressed into the dense clouds necessary for star formation. This creates a fundamental barrier to early structure formation that should have delayed galaxy development by billions of years. Alison Kirkpatrick from the University of Kansas explains that galaxies cannot form quickly because the gas in the early universe is very hot, preventing it from collapsing into galaxies and stars. The thermal energy of the gas creates outward pressure that counteracts the inward pull of gravity, creating a cosmic standoff that should prevent rapid structure formation. The cooling process required to bring gas temperatures down to star-forming levels operates slowly in the expanding universe. As space itself expands, it carries heat away and allows temperatures to drop gradually over cosmic time. This cooling process has its own built-in timeline that cannot be significantly accelerated without changing fundamental properties of the universe. Webb's early galaxies would need the cosmic gas to cool much faster than physics allows, or they would need star formation processes that operate at much higher temperatures than anything we observe in the current universe. Both scenarios require physics that differs fundamentally from our current understanding of thermodynamics and stellar formation. The temperature problem becomes even more severe when you consider that the early universe was also much denser than today. Higher density means more frequent collisions between gas particles, which generates additional heat and further resists the cooling process necessary for star formation. The early cosmos was essentially a pressure cooker that should have prevented rather than encouraged rapid galaxy development. Some theoretical models suggest that dark matter structures could have grown first, creating deep gravitational wells that helped cool gas more efficiently. However, even this process requires time for dark matter to clump together and create the necessary gravitational infrastructure, adding additional constraints to the already impossible timeline. The combination of high temperatures, high pressures, and hostile conditions in the early universe creates a perfect storm of obstacles to galaxy formation. Webb's discovery of massive organized galaxies thriving in these conditions suggests that either our understanding of early universe physics is incomplete, or these galaxies formed through processes we haven't yet discovered. The temperature problem connects directly to another fundamental issue with early galaxy formation: the role of dark matter in providing the gravitational framework necessary for structure development. Dark matter makes up 85% of all matter in the universe, providing the invisible gravitational scaffolding that guides normal matter into galaxies and larger structures. This cosmic framework should take billions of years to develop, yet Webb's early galaxies appear to have formed before dark matter had time to create the necessary infrastructure. Think of dark matter like the steel framework of a skyscraper that must be erected before you can add walls, floors, and windows. The framework provides the essential structure that determines where everything else can be built. In the Cosmic Construction Project, dark matter halos provide the gravitational foundation that determines where galaxies can form and how large they can grow. Dark matter particles interact only through gravity, which means they clump together slowly compared to normal matter that can lose energy through electromagnetic radiation. This slow clumping process follows predictable gravitational dynamics that operate on cosmic timescales measured in billions of years, not the hundreds of millions of years available to Webb's early galaxies. The formation of dark matter halos follows a hierarchical process where small structures merge to form larger ones over cosmic time. First, tiny dark matter clumps form through gravitational instabilities. These small clumps then merge to form larger halos, which eventually become massive enough to trap normal matter and begin forming stars and galaxies. Webb's massive early galaxies would require dark matter halos containing trillions of solar masses worth of invisible matter. Creating halos this massive through the standard hierarchical formation process should take several billion years, even under the most optimistic scenarios. The timeline simply doesn't provide enough cosmic history for these structures to develop. Kirkpatrick explains that instead of galaxies forming quickly, dark matter structure should grow first, and the immense gravity should then funnel gas to the center to grow the first stars and galaxies. This process has its own built-in delays that cannot be circumvented without fundamentally altering how dark matter behaves. The dark matter timeline problem suggests that either these massive early galaxies formed through a completely different process than what we observe in the local universe, or that dark matter itself behaves differently in the early cosmos than our models predict. Both possibilities require major revisions to fundamental physics. Some theoretical proposals suggest that primordial black holes could have provided ready-made gravitational seeds for galaxy formation, bypassing the slow dark matter halo development process. However, these primordial black holes would themselves require exotic physics during the universe's first moments that goes beyond the standard model of cosmology. The dark matter scaffolding problem extends beyond individual galaxies to the large-scale structure of the cosmos. The cosmic web of dark matter filaments that connects galaxies across vast distances should also take billions of years to develop, yet Webb observations suggest this large-scale organization existed much earlier than predicted. These timeline conflicts with dark matter halo formation create yet another fundamental challenge to our understanding of cosmic evolution. The invisible framework of the universe appears to have assembled itself much faster than the laws of physics should allow. But the problems with early cosmic evolution extend beyond just structure formation to the very chemical composition of these impossible galaxies. Webb has detected heavy elements like carbon, oxygen, and iron in galaxies that formed when the universe should have contained only hydrogen and helium. These complex elements are forged in the nuclear furnaces of massive stars and distributed through space when those stars explode as supernovae. The presence of these elements in early galaxies creates a chemical timeline paradox. The Big Bang produced only the three lightest elements: hydrogen, helium, and tiny traces of lithium. Everything heavier than lithium on the periodic table must be created inside stars through nuclear fusion processes that require millions of years to complete. It's like finding a gourmet meal in a kitchen that was just stocked with basic ingredients moments before. Creating heavy elements requires multiple generations of stellar evolution. First-generation stars, called population 3 stars, formed from pristine hydrogen and helium. These massive stars lived fast and died young, exploding as supernovae and spreading the first heavy elements into space. Second-generation stars then formed from this enriched material, creating even more complex elements through their own life cycles. This chemical enrichment process should take billions of years, to produce the levels of heavy elements Webb observed in early galaxies. Each stellar generation requires millions of years to evolve, and the mixing of supernova ejecta throughout galactic gas takes additional time. The early galaxies Webb discovered appear to have skipped several steps in this chemical evolution sequence. The presence of iron in these early galaxies is particularly puzzling because iron forms only in the most massive stars during the final moments before they collapse into black holes or neutron stars. These stellar deaths occur only after millions of years of nuclear burning, and the iron must then be distributed throughout the galaxy by supernova explosions and stellar winds. Webb's spectroscopic observations reveal not just the presence of heavy elements, but abundances that suggest multiple generations of stellar evolution have already occurred in these early galaxies. The chemical signatures indicate a mature stellar population with complex nucleosynthesis histories that should require billions of years to develop. Some of the early galaxies show evidence of dust formation, which requires heavy elements to condense into solid particles in the cold regions between stars. Dust formation adds another layer of complexity to the chemical evolution timeline, requiring not just the creation of heavy elements, but also the specific conditions necessary for these elements to form solid grains. The rapid chemical evolution Webb observed suggests that either the first generation of stars were more massive and shorter-lived than we thought, or that the nuclear processes creating heavy elements operated much faster in the early universe. Both scenarios require significant revisions to our understanding of stellar evolution and nucleosynthesis. The chemical timeline problem compounds all the other impossibilities Webb has discovered. These early galaxies needed time to form their dark matter halos, time to cool their gas, time to form multiple generations of stars, time to synthesize heavy elements, and time to organize into complex structures. The universe simply didn't provide enough cosmic history for all these processes to occur. This chemical maturity connects to another fundamental discovery Webb has made about how these early galaxies interacted with their cosmic environment, creating yet another timeline paradox in the process. Webb discovered that early galaxies were powerful enough to clear vast regions of space around themselves, ionizing gas across distances of millions of light-years, and creating transparent bubbles in what should have been an opaque early universe. This process, called cosmic reionization, should have taken hundreds of millions of years to complete, yet Webb shows it happening much faster than theory predicts. After the Big Bang, the universe went through a period called the Dark Ages, when space was filled with neutral hydrogen gas that blocked most light from traveling freely. Think of it like trying to see through a thick fog that absorbs and scatters photons, making the cosmos opaque to electromagnetic radiation. For light to travel freely, as it does today, this fog needed to be cleared through a process that ionizes the neutral hydrogen. The ionization process requires enormous amounts of ultraviolet radiation to strip electrons from hydrogen atoms, converting neutral gas into a transparent plasma. Early galaxies provided this radiation through the intense light output of their young, massive stars. However, the energy requirements for clearing cosmic-scale regions should have demanded much more time and many more galaxies than Webb observes. Simon Lilly's team discovered that relatively tiny early galaxies created ionization bubbles with radii of 2 million light-years around themselves. To put this scale in perspective, imagine a single house producing enough light to illuminate an entire state. The energy output required for such massive ionization bubbles should have needed much larger galaxies or many more individual sources working together. These transparent bubbles eventually merged with each other to create the completely transparent universe we observe today. However, the merging process should have taken hundreds of millions of years to complete, as more and more galaxies formed and contributed their ionizing radiation to the cosmic clearing project. Webb's observations show that this reionization process was nearly complete by the time the universe was only 1 billion years old, much earlier than previous models predicted. The timeline compression means that early galaxies were either much more numerous, much more massive, or much more efficient at producing ionizing radiation than our theories suggest. The reionization paradox creates another impossible efficiency requirement for early galaxies. They needed to convert their gas into stars fast enough to produce the necessary ultraviolet radiation, while simultaneously growing massive enough to power the ionization process, all while organizing themselves into the complex structures Webb observes. Each ionizing photon can only convert one hydrogen atom from neutral to ionized, which means the total energy budget for cosmic reionization is enormous and precisely calculable. Early galaxies would need to produce far more ionizing photons per unit of stellar mass than galaxies in the local universe, requiring either different stellar populations or more efficient energy production processes. The rapid reionization Webb discovered suggests that the early universe was a much more active and energetic place than we believed. The combination of massive early galaxies, rapid star formation, efficient energy production, and large-scale ionization creates a picture of cosmic evolution that operates at speeds that challenge fundamental physics. This reionization timeline problem represents the final piece of evidence that Webb's discoveries create an interconnected web of impossibilities that cannot be explained by minor adjustments to existing theories. The early universe Webb reveals operates according to rules that differ fundamentally from everything we observe in the cosmos today. But there may be alternative explanations that could resolve some of these timeline paradoxes. What if the massive black holes Webb discovered didn't grow from stellar collapse but existed from the universe's first moments? Primordial black holes represent a radical alternative to our understanding of cosmic evolution, potentially explaining how massive structures could form so quickly in the early universe without violating the laws of physics. Unlike stellar black holes that form when massive stars collapse at the end of their lives, primordial black holes could have formed directly from the extreme conditions during the universe's first fraction of a second. These ancient objects would have existed as ready-made gravitational seeds, providing the foundation for rapid galaxy formation without requiring the slow buildup of dark matter halos. Think of stellar black holes like oak trees that grow slowly from acorns over many decades. Primordial black holes would be like discovering fully grown sequoias that were somehow planted as mature trees from the very beginning. They bypass the entire growth process by existing from cosmic dawn, ready to immediately begin attracting matter and building galaxies around themselves. Pablo Perez Gonzalez's team found that about 30% of the mysterious early light sources Webb detected have characteristics consistent with primordial black holes rather than early stars. These objects appear point-like rather than extended, suggesting they might be individual massive black holes rather than distributed stellar populations across entire galaxies. If primordial black holes provided the gravitational anchors for early galaxy formation, they could explain many of Webb's impossible discoveries. The massive early galaxies wouldn't need to wait billions of years for dark matter halos to form through slow hierarchical assembly. Instead, they could begin growing immediately around these pre-existing gravitational wells. Primordial black holes could also explain the rapid chemical evolution Webb observed in early galaxies. These ancient objects would have immediately begun accreting surrounding gas, triggering intense star formation in their vicinity. The resulting stellar populations could live, die, and enrich the surrounding gas with heavy elements much faster than conventional galaxy formation models predict. The accretion process around primordial black holes generates enormous amounts of energy that could power the intense luminosity Webb observed in early cosmic sources. This energy output could also drive the rapid ionization of surrounding gas, helping to explain how early galaxies cleared such large regions of space around themselves. However, primordial black holes require very specific conditions during the universe's first moments to form. The density fluctuations in the early cosmos would need to be much larger than our current models predict, requiring exotic physics during the inflationary period immediately after the Big Bang. The primordial black hole hypothesis also makes specific predictions that can be tested with future Webb observations. These objects should leave characteristic signatures in the cosmic microwave background radiation and create distinctive patterns in the large-scale structure of the universe that differ from conventional dark matter-driven formation. While primordial black holes offer a potential explanation for some of Webb's discoveries, they represent just one of several alternative theories that attempt to resolve the timeline paradoxes. Other proposals challenge even more fundamental assumptions about cosmic evolution, including the very nature of cosmic redshift itself. What if distant galaxies aren't racing away from us through expanding space, but their light is simply losing energy during its journey across the cosmos? The tired light theory, first proposed by astronomer Fritz Zwicky in the 1920s, suggests that cosmic redshift might not indicate universal expansion, but rather a fundamental property of light, traveling through space over vast distances. In the tired light model, photons gradually lose energy as they traverse the universe, shifting toward longer, redder wavelengths without requiring space itself to expand. Think of it like a marathon runner who starts the race at full speed but gradually slows down over the course of 26 miles. The light begins its journey with high energy and short wavelengths, but arrives at our telescopes exhausted and redshifted. This energy loss could occur through interactions with virtual particles in the quantum vacuum, scattering off cosmic dust, or through other mechanisms that operate over cosmic distances. Einstein himself suggested that light might experience energy loss proportional to the distance it travels, though he didn't specify the exact physical mechanism responsible. Recent Webb observations have renewed interest in tired light theory because they seem to support some of its predictions while contradicting aspects of expanding universe models. Lior Shamir from Kansas State University analyzed redshift data from over 30,000 galaxies and found patterns that align better with tired light than with cosmic expansion. The tired light model eliminates many of the timeline problems Webb discovered because it doesn't require the universe to be only 13.8 billion years old. If cosmic redshift reflects energy loss rather than expansion, the universe could be much older or even eternal, providing unlimited time for massive galaxies and supermassive black holes to form through conventional processes. Under tired light theory, the massive early galaxies Webb discovered wouldn't represent impossible rapid formation in a young universe. Instead, they would be mature objects in an ancient cosmos, where distance, not time, creates the redshift we observe. The apparent youth of these galaxies would be an illusion created by misinterpreting redshift as expansion rather than energy loss. This alternative explanation also resolves the Hubble tension because there would be no universal expansion to measure. The conflicting expansion rates that have puzzled cosmologists for decades disappear if redshift indicates tired light rather than recession velocity. The measurement disagreements become irrelevant when the fundamental interpretation changes. Shamir's analysis found that galaxies rotating in opposite directions relative to the Milky Way show different redshift patterns, reflecting Earth's motion through space rather than universal expansion. This asymmetry supports tired light models while challenging the assumption that redshift indicates recession due to expanding space. However, tired light theory faces significant challenges from other astronomical observations. The cosmic microwave background radiation, the abundance of light elements, and the detailed patterns of large-scale structure all seem to require the Big Bang model with cosmic expansion. Reconciling tired light with these observations requires additional theoretical modifications. The theory also struggles to explain the time dilation observed in distant supernovae, where explosive events appear to unfold more slowly at higher redshifts. This time dilation effect provides strong evidence for cosmic expansion that tired light models have difficulty reproducing without additional assumptions. Despite these challenges, Webb's discoveries have forced cosmologists to reconsider fundamental assumptions about cosmic redshift and expansion. The massive early galaxies and impossible timelines revealed by the telescope suggest that our interpretation of cosmic observations might need radical revision, but even more dramatic alternatives to standard cosmology have emerged from Webb's data. Webb detected active star formation occurring when the universe was only 100 million years old, during an epoch when the cosmos should have been too hot and chaotic for stellar nurseries to exist. The telescope revealed young, massive stars blazing with intense blue light from redshift 25, pushing the boundaries of when star formation could theoretically begin. At 100 million years after the Big Bang, the universe was still recovering from its violent birth. Gas temperatures remained scorching hot. Matter was distributed much more uniformly than today, and the heavy elements necessary for efficient star formation hadn't yet been created by previous stellar generations. These conditions should have prevented the collapse of gas clouds into the dense cores needed for nuclear ignition. Think of trying to build a campfire during a hurricane with wet wood and no kindling. The environmental conditions work against every step of the process, making ignition nearly impossible. Early universe star formation faced similar obstacles. Hot gas resisted gravitational collapse, turbulent motions prevented stable cloud formation, and the lack of heavy elements eliminated efficient cooling mechanisms. Normal star formation requires gas clouds to cool down and collapse under their own gravity until core temperatures reach 10 million degrees, hot enough to ignite nuclear fusion. In the early universe, the background gas temperature was already so high that additional cooling became extremely difficult, creating a fundamental barrier to stellar birth. The first generation of stars, called Population 3 objects, should have been significantly different from the stars we observe today. These primordial giants would have contained only hydrogen and helium, making them extremely massive and short-lived compared to metal-rich stars that form in the current universe. Their brief lifespans should have created a natural delay in building up large stellar populations. Webb's observations suggest that early star formation proceeded much more rapidly and efficiently than these theoretical predictions. The blue ultraviolet light the telescope detected indicates the presence of massive, hot, young stars that require rapid formation and high-efficiency conversion of gas into stellar material. Some research teams propose that early star formation operated through a bursty mode where periods of intense stellar birth alternated with dormant phases. During these bursts, galaxies could form stars much faster than the steady, continuous process we observe in local galaxies, temporarily overcoming the hostile conditions of the early universe. Claude-André Faucher-Giguère from Northwestern University suggests that early galaxies experienced rapid bursts of star formation after millions of years of dormancy. These intense episodes could create the bright, massive stellar populations Webb observed, without requiring sustained star formation over billions of years. The bursty formation model proposes that stellar winds and supernova explosions would periodically clear gas from early galaxies, shutting down star formation temporarily. When the gas eventually cooled and fell back into the galaxy, it would trigger another intense burst of stellar birth, creating a cosmic heartbeat of stellar formation. However, even the bursty formation model struggles to explain the sheer number and brightness of early stars Webb discovered. The energy output from these early stellar populations exceeds what even optimistic burst models predict, suggesting that fundamental aspects of stellar physics might operate differently in the primordial universe. The rapid early star formation Webb observed compounds all the other timeline problems by requiring not just fast galaxy assembly, but fast stellar evolution to create the chemical elements and energy output necessary for the complex structures the telescope has revealed. This stellar formation mystery connects directly to broader challenges facing the entire framework of modern cosmology. Lambda cold dark matter cosmology, the theoretical framework that has guided our understanding of the universe for decades, faces its greatest challenge from Webb's impossible discoveries. This standard model, built on dark energy, cold dark matter, and conventional physics, simply cannot accommodate the massive early galaxies and rapid evolution the telescope has revealed. The Lambda CDM model makes specific, quantitative predictions about how quickly structures can form in the early universe. These predictions arise from fundamental physics governing how dark matter clumps together, how gas cools and forms stars, and how galactic structures assemble over cosmic time. Webb's observations violate nearly every one of these carefully calculated predictions. Think of the Standard Model like a detailed recipe that specifies exactly how long each step should take to create the final cosmic dish. The recipe calls for billions of years of slow simmering to develop complex flavors and textures. Webb discovered that somehow the universe produced a gourmet meal in minutes using only basic ingredients and a simple microwave. Mike Boylan-Colchin warned that if Webb's mass measurements prove correct, fundamental changes to the reigning model of cosmology would be required. The discoveries don't represent minor adjustments to existing theory, but rather wholesale revisions to our most basic assumptions about how the universe works. The Standard Model predicts that only a small fraction of the universe's matter should be contained in massive galaxies during the first billion years after the Big Bang. Webb discovered roughly twice as many massive early galaxies as the model allows, with some individual objects exceeding the theoretical maximum mass for their epoch by factors of 10 or more. These violations extend beyond just galaxy masses to include formation timescales, chemical evolution rates, and structural organization that all conflict with Lambda CDM predictions. It's not a single observation that contradicts theory, but rather a systematic pattern of violations across multiple independent measurements and analysis techniques. The crisis deepens because the Standard Model isn't just a loose collection of ideas, but rather a tightly integrated theoretical framework where each component depends on the others. Changing one aspect to accommodate Webb's discoveries inevitably creates conflicts with other well-established observations that previously supported the model. For example, modifying the dark matter properties to allow faster structure formation might resolve the early galaxy problem, but would create new conflicts with observations of the cosmic microwave background, the large-scale structure of the universe, or the abundance of light elements created during Big Bang nucleosynthesis. Similarly, changing the expansion history of the universe to provide more time for early structure formation would affect the predicted age of the oldest stars, the timing of cosmic reionization, and the relationship between distance and redshift that underlies much of observational cosmology. James Peebles, a Nobel laureate and pioneer of modern cosmology, emphasizes that science thrives on doubt and that Webb's findings present an opportunity for progress rather than a crisis. However, the scope and scale of the violations suggest that any resolution will require fundamental rather than incremental changes to our cosmic worldview. The Standard Model crisis extends beyond just theoretical predictions to observational techniques and measurement methods that have been refined over decades. Webb's discoveries suggest that some of our most basic assumptions about interpreting cosmic observations might be flawed from the ground up. This systematic challenge to Lambda CDM connects to other anomalies Webb has discovered in cosmic measurements, including unexpected patterns in how galaxies appear at different distances that contradict fundamental assumptions about space and time. Webb discovered that distant galaxies appear larger in the sky than expanding universe models predict, creating a measurement crisis that challenges one of the fundamental assumptions underlying Big Bang cosmology. The angular sizes of these faraway objects suggest that space itself might not be expanding, as we've assumed for nearly a century. When space expands, it creates a specific relationship between an object's distance, its actual size, and how large it appears in the sky. Think of watching a balloon inflate while a toy soldier sits on its surface. As the balloon grows, the toy soldier moves farther away, but should also appear smaller due to the increasing distance created by the expanding surface. In an expanding universe, distant galaxies should appear smaller than they would in a static cosmos, because the expansion of space stretches the light path and affects the relationship between distance and angular size. This prediction is fundamental to Big Bang cosmology and has been used to interpret cosmic observations for decades. However, Webb's measurements of distant galaxy angular sizes don't match expanding space predictions. The galaxies appear roughly 10 times larger than Big Bang models predict they should at their observed redshifts. This discrepancy is systematic and consistent across multiple independent measurements, ruling out random measurement errors. The angular size problem connects directly to the Doppler interpretation of cosmic redshift that supports tired light theory. If redshift indicates light energy loss rather than cosmic expansion, then the relationship between distance, redshift, and angular size would follow completely different mathematical rules that align much better with Webb's observations. Biblical cosmologist Danny Faulkner analyzed Webb's data and found that galaxy angular sizes average about 0.2 arcseconds at high redshifts, exactly matching predictions from non-expanding Doppler models while contradicting Big Bang expectations by factors of 10. This represents one of the most precise observational tests of cosmic expansion ever conducted. The angular size measurements are particularly significant because they don't depend on complex assumptions about stellar populations, galaxy evolution, or dark matter physics. They represent direct geometric observations that test the fundamental assumption of expanding space through basic trigonometry and light travel. If space is not expanding, then cosmic redshift must be explained through alternative mechanisms like tired light, intrinsic redshift, or other physical processes that don't require the fabric of space itself to stretch over cosmic time. These alternatives would eliminate the need for dark energy, the mysterious force supposedly driving accelerated expansion. The angular size anomaly also affects brightness measurements, with distant galaxies appearing brighter than expanding universe models predict. The combination of larger angular sizes and higher brightness values creates a consistent pattern that supports static universe interpretations while challenging expansion-based cosmology. These geometric measurements represent some of the most direct tests of cosmic expansion possible, bypassing many of the complex astrophysical assumptions that complicate other cosmological observations. The fact that they systematically contradict expansion predictions suggests a fundamental problem with our interpretation of cosmic structure. The angular size crisis extends beyond individual galaxy measurements to affect our understanding of cosmic geometry, the relationship between space and time, and the basic framework we use to interpret astronomical observations across the electromagnetic spectrum. But the measurement anomalies Webb discovered extend even deeper into the timeline of cosmic evolution, revealing patterns that suggest the universe's history might be fundamentally different from everything we've believed about cosmic development. According to Big Bang theory, the universe should have experienced a prolonged period of darkness, lasting hundreds of millions of years, when no stars existed and no light illuminated the cosmos. Webb's discoveries suggest these dark ages never happened, revealing instead a universe that was actively forming stars and galaxies much earlier than theory allows. The Dark Ages were supposed to begin about 400,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. This process, called recombination, should have made space transparent for the first time, but also eliminated the free electrons needed for continued energy production through electromagnetic processes. Without energy sources to prevent gravitational collapse, the universe should have entered a dark period where only gravity operated to slowly pull matter together into the first cosmic structures. This era should have lasted until the first stars finally formed hundreds of millions of years later, ending the darkness with cosmic dawn. Think of the Dark Ages like a power outage in a city that should last for hours, while repair crews slowly restore electricity to different neighborhoods. The universe was supposed to go dark after recombination and remain dark until the first stellar power plants came online to illuminate space once again. Webb discovered bright, organized light sources at redshift 25, when the universe was only 100 million years old. This represents cosmic dawn, arriving 3 to 4 times earlier than standard models predict, compressing the supposed dark ages into a much shorter period than theory allows. The discovery of active star formation at redshift 17 and beyond suggests that the universe never experienced the extended dormant period that Big Bang cosmology requires. Instead of dark ages lasting hundreds of millions of years, Webb reveals a cosmos that became active and luminous almost immediately after recombination. Emma Chapman from the University of Nottingham noted that the discovery of such massive galaxies so soon after the Big Bang suggests that the dark ages may not have been so dark after all. The universe appears to have been awash with star formation far earlier than we thought, fundamentally altering our timeline of cosmic evolution. The absence of extended dark ages eliminates one of the key predictions of Big Bang cosmology and suggests that the early universe operated according to very different physical principles than we've assumed. The rapid transition from recombination to active star formation requires processes that bypass the slow gravitational assembly predicted by standard models. If the dark ages were much shorter or non-existent, then the timeline problems Webb discovered with early galaxy formation become even more severe. The universe would have had even less time than previously calculated to assemble the massive organized structures the telescope observes. The missing dark ages also affect our understanding of cosmic reionization, the process that made the universe transparent to most wavelengths of light. If star formation began much earlier than expected, then reionization would also have started earlier, requiring a complete revision of the timeline governing cosmic transparency. This early cosmic activity suggests that either the conditions immediately after recombination were very different from what we believe, or that alternative energy sources beyond stellar formation provided the illumination Webb observes in the supposed dark ages. The elimination of the dark ages represents another fundamental violation of Big Bang predictions, adding to the growing list of cosmic processes that appear to operate faster, earlier, and more efficiently than standard cosmology allows. But Webb's discoveries reveal even more dramatic deviations from expected cosmic behavior. Webb captured images of massive galaxies in the early universe that show clear evidence of recent mergers and ongoing galactic cannibalism, processes that should require billions of years to complete, but appear to have happened in cosmic fast-forward during the universe's infancy. These galactic collisions represent another timeline impossibility that challenges our understanding of cosmic evolution. Galaxy mergers are among the most violent and complex events in the universe, requiring precise gravitational choreography as two massive stellar systems spiral together over hundreds of millions of years. The process involves multiple stages: initial gravitational attraction, orbital decay, tidal disruption, and final coalescence into a single larger system. Think of galactic mergers like two cities slowly growing toward each other over centuries until they eventually combine into a single metropolis. The process requires time for infrastructure to develop, populations to migrate, and systems to integrate. Webb discovered cosmic cities that appear to have merged overnight in a universe that was barely old enough for neighborhoods to form. The early massive galaxies Webb observed show distorted shapes, elongated structures, and irregular morphologies that are characteristic signatures of recent merger activity. These gravitational disruptions require the galaxies to have encountered each other, interacted over extended periods, and completed complex dynamical processes within the limited time available in the early universe. Current models predict that major galaxy mergers should be rare in the early cosmos, because galaxies would be widely separated by cosmic expansion and would need significant time to grow large enough to gravitationally attract each other across vast distances. The merger process itself adds additional time requirements that compound the timeline problems. Webb's observations reveal not just isolated merger events, but systematic evidence of widespread galactic cannibalism throughout the early universe. Large galaxies appear to be actively consuming smaller companions, building up mass through accretion processes that should require much longer timescales than the young universe provides. The rapid merger activity Webb discovered helps explain how early galaxies could achieve such massive sizes so quickly, but it creates new problems by requiring the pre-existence of numerous smaller galaxies that could serve as merger partners. These building block galaxies would themselves need time to form before becoming available for incorporation into larger systems. The gravitational dynamics governing galaxy mergers operate at speeds determined by fundamental physics and cannot be significantly accelerated without changing the basic laws of gravity. The orbital periods, tidal forces, and dynamical friction that control merger timescales are among the most precisely calculated processes in astrophysics. Webb's merger observations suggest that either gravitational interactions operated much more efficiently in the early universe, or that the initial distribution of matter was very different from what standard models predict. Both possibilities require significant modifications to our understanding of cosmic structure formation. The rapid galactic cannibalism also affects stellar formation within the merging systems, triggering intense bursts of star formation that could contribute to the impossible luminosity levels Webb observed in early galaxies. These merger-driven starbursts add another layer of complexity to the timeline challenges. The prevalence of early mergers Webb discovered indicates that the universe was a much more dynamic and active place during its first billion years than we previously believed, with massive gravitational interactions occurring on timescales that seem impossible under current physics. This accelerated cosmic violence connects to another fundamental problem Webb has revealed: the extreme brightness levels of early galaxies that exceed what should be physically possible given the constraints of stellar formation and energy production in the primordial universe. The early galaxies Webb discovered shine with luminosities that violate fundamental limits on energy production in stellar systems. These cosmic beacons blaze forth with brightness levels that would require more massive stars, more efficient nuclear fusion, or completely unknown energy sources to explain their impossible radiance in the infant universe. Stellar luminosity depends on mass, with the brightest stars burning through their nuclear fuel at rates that limit both their energy output and their lifespans. The most massive stars that can theoretically exist would produce specific maximum brightness levels that cannot be exceeded without violating the physics of nuclear fusion and stellar structure. Early galaxies containing billions of stars should have predictable total luminosity based on the combined light output of their stellar populations. Webb discovered early galaxies that exceed these theoretical brightness limits by factors of 10 or more, suggesting they contain stellar populations that shouldn't be physically possible. Think of stellar brightness like the maximum wattage a light bulb can produce before it burns out. You can't exceed certain brightness levels without changing the fundamental design of the bulb or discovering entirely new ways to generate light. Early galaxies appear to be cosmic light bulbs that somehow exceed every known brightness limit. The extreme luminosity problem becomes more severe when you consider that early universe stars should have been less efficient at producing light than modern stellar populations. The lack of heavy elements in primordial gas should have created stars with different internal structures and energy production mechanisms that generate less light per unit of mass. Webb's brightest early galaxies show luminosity levels that would require stellar populations with impossible characteristics, stars more massive than the theoretical upper limit, nuclear fusion processes that operate more efficiently than physics allows, or energy sources beyond conventional stellar burning. Some researchers propose that supermassive black holes at galactic centers might contribute to the extreme brightness through accretion-powered emission. However, the black holes themselves represent another impossibility, as we've seen, and their feeding processes should create feedback effects that shut down rather than enhance overall galactic luminosity. The brightness crisis extends beyond individual galaxies to the collective light output of the early universe. Webb's observations suggest that the cosmic background light from early epochs should be much brighter than we observe today, creating a paradox known as Olbers's paradox on a cosmic scale. If the early universe contained so many extremely bright galaxies, their combined light output should have created a bright background glow visible in the night sky today. The absence of this excess background light suggests either that our distance measurements are wrong, that light is being absorbed by unknown processes, or that the brightness measurements themselves indicate non-standard physics. The extreme early galaxy luminosity also affects cosmic reionization by providing far more ionizing radiation than models predict. This excess energy could explain the rapid clearing of cosmic hydrogen Webb observed, but it creates new problems by requiring energy production mechanisms that exceed theoretical limits. Claude-André Faucher-Giguère suggests that the brightness problem might be resolved through bursty star formation that concentrates stellar energy output into brief periods of intense luminosity. However, even these burst models struggle to account for the sustained high brightness levels Webb observes across multiple cosmic epochs. The luminosity violations Webb discovered represent some of the most direct challenges to stellar physics and energy production mechanisms. Unlike other cosmological problems that might be resolved through exotic matter or modified gravity, the brightness crisis requires revisions to fundamental physics governing how stars shine. This energy production crisis connects to proposals for entirely new physical forces and particles that might operate in the early universe, suggesting that the cosmos once functioned according to very different physical laws than those governing the universe today. To explain Webb's impossible discoveries, physicists are proposing exotic forces and particles that operated in the early universe but have since disappeared or become inactive. These theoretical additions to the standard model of particle physics represent desperate attempts to preserve our cosmic timeline by introducing completely new physics. Mike Boylan-Colchin suggested that one of the most extreme possibilities for explaining rapid early galaxy formation is that the universe was expanding faster shortly after the Big Bang than we predict, which might require new forces and particles beyond everything we currently understand about the fundamental structure of reality. Think of the early universe like a construction site, where workers had access to advanced tools and techniques that are no longer available today. These cosmic construction crews could build massive structures using methods that became obsolete or impossible once conditions changed, leaving behind achievements that seem impossible given current capabilities. Early dark energy represents one proposed new component that could have accelerated cosmic expansion during the first billion years, providing more time for structure formation by stretching the cosmic timeline. This mysterious energy field would need to operate very differently from the dark energy driving current cosmic acceleration. Mark Kamionkowski from Johns Hopkins University suggests that exotic particles with properties unlike anything in the standard model might have dominated physics during the universe's infancy. These particles could have enhanced gravitational attraction, modified stellar formation processes, or provided alternative energy sources for cosmic structure development. Changing electron mass represents another exotic possibility, where fundamental particles had different properties in the early universe. If electrons were lighter or heavier in the past, it would affect atomic structure, chemical bonding, and stellar physics in ways that could accelerate galaxy formation and energy production. Primordial magnetic fields offer yet another avenue for new physics, suggesting that the early universe contained much stronger magnetic fields than exist today. These fields could have guided matter assembly, enhanced star formation efficiency, and created the organized structures Webb observes through electromagnetic forces. The proposals for new physics aren't just minor additions to existing theory, but rather fundamental modifications to our understanding of how forces, particles, and fields operate. They suggest that the universe once functioned according to a completely different set of physical laws that somehow transitioned to current physics. Exotic matter with negative pressure or unusual gravitational properties could have accelerated structure formation by creating stronger, attractive forces than normal matter generates. This exotic matter would need to disappear or become inactive after serving its cosmic construction purpose. Modified gravity theories propose that gravitational attraction operated differently in the early universe, perhaps growing stronger at large scales or operating faster than general relativity predicts. These modifications would need to transition smoothly to standard gravity as the universe evolved. The particle physics required to explain Webb's discoveries pushes far beyond the standard model into realms of pure theoretical speculation. The proposed particles and forces have no experimental evidence supporting their existence and would require revolutionary advances in our understanding of fundamental physics. String theory, extra dimensions, and quantum gravity effects represent additional exotic possibilities for early universe physics. These advanced theoretical frameworks might provide mechanisms for accelerated cosmic evolution that operate only under the extreme conditions present during the universe's first billion years. The requirement for new forces and particles to explain Webb's observations suggests that either our cosmic timeline is fundamentally wrong, or that the universe once operated according to physics so exotic that it bears little resemblance to the cosmos we observe today. These exotic physics proposals connect directly to evidence, suggesting that the expansion rate of the universe itself might have been very different in the past, requiring yet another layer of unknown physics to explain cosmic evolution. The universe demands a new origin story, one that can accommodate massive early galaxies, rapid cosmic evolution, and impossible timeline compressions, while explaining why these discoveries conflict so dramatically with our most fundamental theories. This new cosmic narrative will likely combine elements from multiple alternative theories, while introducing physics we haven't yet discovered. The new model might begin not with a singular Big Bang, but with a pre-existing cosmic state that provided unlimited time for structure formation before transitioning to the expanding universe we observe today. This would eliminate timeline constraints while preserving the observational evidence for cosmic expansion and cooling. Hybrid cosmologies that combine steady-state creation with Big Bang evolution offer one path forward, suggesting that the universe underwent different phases of evolution governed by different physical laws. The early phase could have operated under conditions that allowed rapid structure formation before transitioning to standard physics. Multi-dimensional models propose that early cosmic evolution occurred in higher dimensional spaces where different physics allowed impossible structure formation rates. As the universe evolved, it transitioned to our current three-dimensional limitations, preserving early structures while preventing further impossible evolution. The new cosmic story might feature variable fundamental constants, with the strength of gravity, the speed of light, or the mass of particles changing over cosmic time in ways that created windows of opportunity for accelerated structure formation during specific cosmic epochs. Quantum cosmology could provide the framework for pre-existing cosmic organization, suggesting that the universe inherited structure from underlying quantum fields rather than building it up slowly through gravitational assembly. This quantum inheritance would explain rapid organization without violating physical laws. The role of consciousness and information in cosmic evolution represents another frontier that might need exploration. If the universe operates more like a computational system than a mechanical one, then cosmic evolution could follow algorithmic rules that permit rapid structure formation under specific conditions. Dark sector physics offers yet another avenue, proposing that most cosmic evolution occurs through interactions between unknown particles and forces that operate parallel to the standard model physics we observe. These dark interactions could drive rapid structure formation, while remaining mostly invisible to current observations. The new origin story will need to explain not just Webb's impossible discoveries, but also why our current theories worked so well for describing the local universe, while failing catastrophically for early cosmic evolution. This suggests that physics itself might be contextual, operating differently under different cosmic conditions. Revolutionary measurement techniques might reveal that our interpretation of cosmic observations contains systematic errors that created the illusion of impossible early evolution. Perhaps redshift, distance measurements, or time itself operate differently than we've assumed, making apparently impossible observations actually quite normal. The ultimate cosmic story might combine multiple exotic physics proposals: primordial black holes, providing gravitational seeds; tired light, explaining redshift; variable expansion, creating time windows; new forces accelerating evolution; and pre-existing cosmic states providing unlimited history. Whatever new model emerges will need to be more than just theoretically consistent. It must make specific, testable predictions that can be verified or falsified through future observations. The James Webb Space Telescope will continue collecting data that will either support or eliminate various proposals for new cosmic physics. The rewriting of our origin story represents more than just academic exercise. It touches on fundamental questions about the nature of existence, the role of time in cosmic evolution, and humanity's place in a universe that might be far stranger and more wonderful than we ever imagined. We stand at a cosmic crossroads, where the universe itself is forcing us to expand our understanding of reality. The impossible discoveries Webb has revealed suggest that we're living in a cosmos that operates according to rules we haven't yet learned to recognize. The greatest adventure in human understanding is just beginning.